This is part 3 in our lesson on transformations of functions, and today we're going to talk about dilations. A dilation is a transformation that changes the size of a particular function, but it doesn't change the shape. If it's a v parent function, it's going to remain a v after the dilation. It's just going to make it either a wide or a skinny v. If it's a parabola, a U-shape, it's still going to be a U-shape, but it's going to either be a wide U or a skinny U. So that's the kind of thinking that's going to take place in this section. My goal is to, hopefully after this lesson, you'll be able to identify when you do have what is known as vertical stretch or what is known as vertical compression, and then what is horizontal stretch. How do you know you have horizontal stretch of a parent or horizontal compression? So that'll be the focus of today's lesson. So let's just get right into it. These are some very important points, principles regarding dilations. And if you notice, it's really all about this number that I'm calling A. This is in front of the parent function y equals x, that line. If there's a number there in front of x, besides 0 of course, a number here in front of the absolute value, a number here in front of x squared, when that number is greater than 1, we have what is known as vertical stretch. And you can think of that as taking the top part of a v, for example, and pulling upward toward the positive y-axis, and think of that making the V-shape skinnier. Or that would also be true for a parabola. Just take the top of the parabola and pull it, stretch it upward, and that would cause it to become what we would call skinnier. Alright, so here's some examples of transformations, dilations that involve vertical stretch. Notice the number in front of x. Notice the number in front of the absolute value of x, in front of x squared. In all of these cases, the number a is greater than 1. So you know you're going to be dealing with vertical stretch. Over here, some examples of the a number being between 0 and 1. So in other words, it's a fraction. Whenever we have this case, then we have what is known as vertical compression. So that's one way of thinking about that is think about pushing down on a graph and causing it to spread out. As the force is being pushed down on a V shape or a U shape, it causes it to spread out, okay, get fatter. So let's just take a look at some examples. You're going to be doing some of these in your homework. I just wrote of course, there's the definition of a dilation again. Your book is going to want you to describe, first of all, the dilation in each function as it relates to its parent graph. So let's just take this first example, y equals 2x squared. Well, that is a dilation of the parent function y equals x squared. Okay? So the bottom line is, at this point anyway, you have 3 parent functions to choose from. Y equals x squared, y equals the absolute value of x, and y equals x. Alright, we're going to add to this list as we get further into the year, but at this point the answer to this part will be one of these 3 functions. These are the parent functions that we know so far. Alright, and I notice that the number that we call a in front of x squared is greater than 1. So that creates what we call vertical stretch, or in this case I'm phrasing it as it's stretched vertically. Alright, so we got a graph. You don't have to do the parent function in these cases, but I'm just going to put it up here just to illustrate again what we mean by vertical stretch. So these black dots represent points on the parent function y equals x squared. Now let's come up with a table to represent this function y equals 2x squared. Of course, if I do an input of 0, I get an output of 0. If I do an input of 1, I do 1 squared first. That's 1 times 2 is 2. Alright, so 1, 2. And then symmetry created by the y-axis means that I can match that point up on the left side of the y. Let's do one more point. If I do an input of 2, 2 squared is 4, and 4 times 2 is 8. So 2, 8 is on this transformation graph. And so the black, as you can see, it's slight, but the black is going to be a little bit wider. The red is going to be a little skinnier. So this is a good example of illustrating what we call vertical stretch. It's a skinnier version of the parent. Okay, so that would be your final answer. You have to describe the dilation. We did that, and then graph the function. You do not have to put the parent points. I mean, if you want to, that's fine, but it's not required. Okay, well, let's take a look at another example. This time you notice the A value is between 0 and 1. So this is still a dilation of that same parent function, but this time, instead of stretching vertically, we're going to be compressing vertically. Okay, so once again, we'll show the parent points. All right, just so we can have something to compare. And now let's come up with a table of values for y equals 1/2 x squared. Of course, we'll have the origin. Let's use some numbers, multiples of 2, to make our plotting a little bit easier. We'll do 2 squared, which is 4. 4 times 1/2 is 2. So 2, 2 is on our graph, and then so is negative 2, 2. Let's try 4 as an input. 16 times 1/2 is 8, so the point 48 is on our graph, and symmetry means we have another point. So you can see that the red is a wider version of the black parent. Okay, so compressing, just think of we're pushing the parent downward. It's one way of looking at it. When you push the parent downward, it causes it to spread out. It causes it to get fatter. Okay, so we looked at an example of vertical stretch, vertical compression, okay, and it's all about this number in front of x squared, or it's also true, as you can see my my next slide here, that's talking about horizontal stretch. I'll go back to vertical stretch, vertical compression. We've only looked at the parent y equals x squared, but that's also true for absolute value. Notice that, and also for that linear function. So just wanted to point that out. I'm only using the y equals x squared, but it's true for the others as well. All right, so we've talked about vertical stretch and compression. Now let's talk about horizontal stretch and compression. Well, as you notice, we're still focused on this number that I'm calling A, but notice where it is now. Okay, draw a distinction between this example and now I've got this number I've called A inside either parentheses, or in the case of absolute value, it would be inside the absolute value. Okay, so this is going to give me either horizontal stretch or compression, and I've given you some really good information here. If that A number is greater than 1 and it's inside either parentheses or absolute value, you're going to have horizontal compression. Okay, here's a couple examples. If that number is a fraction inside parentheses or absolute value, as I've shown here, you're going to have horizontal stretch. Okay, horizontal stretch is pulling on the sides of your graph, making it wider. Horizontal compression is just the opposite. It's pushing in on the sides of your graph, making it skinnier. All right, so let's take a look at a couple examples. Once again, I'm using that parent y equals x squared. And since the A number is inside parentheses and it's greater than 1, then I have horizontal compression. Okay, so once again, we'll just look at our parent parabola using black dots, and let's come up with a table of values for the given function 0, 0. If I input 1, I get 2 squared, which is 4, and match that up. If I input 2, I get 4 squared, which is 16. Well, you can tell that's getting up there pretty fast. So this is going to be a very skinny version. Try to freehand this best I can, but that's not real good. This is going to be a skinny version of the parent. And this is what horizontal compression does. It pushes in. It's like pushing in on the sides of the parent function, creating a skinnier version of the parent. Okay, well, let's take a look at what we mean by horizontal stretch. Notice the A number inside parentheses. It's between 0 and 1, and that's a giveaway that you're dealing with horizontal stretch. We're still dealing with the parent y equals x squared. And let's put the points for the parent function up here again so we can see how it relates. And so let's build a table of values for this given function. Again, we got 0, 0. We'll use some multiples of 2 to make this easy. So we're going to do parentheses first. 1/2 times 2 is 1. 1 squared is still 1. So I got the point 2, 1. And then that means negative 2, 1 will be on our graph. Let's use 4 as an input. 1/2 times 4 is 2. 2 squared is 4. So we'll plot the point 4, 4. And we'll do the same thing on the other side. Well, you can probably tell that the red is a wider version of the black parent. And this is an example of horizontal stretch. We're just taking the parent. Stretch horizontally means we're pulling on it from the sides, and that's how we get this red transformed parent function, this dilated parent function. Okay, so that is it. If you haven't already, most of you have already done the problems 8 to 13. Some of the classes did, some didn't, but I'll go ahead and include it here just in case. All of this will be checked the next time, and if there are any questions, feel free to email me or come to academic support.